Okay, the next trend we're going to talk about is ionization energy. Ionization energy is simply the energy required to remove an electron. Okay, and it always takes energy to remove an electron, even for those elements that really want to have a full outer shell. It does take some energy to make that happen. So the term is a little bit misleading because it's ionization energy, but it really should be cation energy, because it's only the energy required to make a positive ion, right? Because it's the energy required to remove an electron, and when an electron is removed, I end up as a positive ion. Okay, so let's take a look at the trends. So let's think first about which elements want to, it would be easiest to remove an electron from. So let's think first about the noble gases. The noble gases have a full octet, right? They are very stable. Is it going to be easy to take an electron from them? No, it's going to require a high energy, a high ionization energy. Now, what about something like sodium? It's got one valence electron, and if it loses that outer shell, it becomes the electron configuration of neon, which is very stable. So this is not going to take much energy at all. So as you can see, the ionization energy is going to increase as we go across the periodic table. Now what about as we go down? If we go down, what's happening when we do that is when we add another shell, each time we go down a period on the periodic table, we're adding an additional shell. And here, when we think about Coulomb's law, Q1 over Q2 over distance squared, what's happening is we are increasing the distance between the nucleus, right? Each time we do that. So the further away the opposite charges are, the less strong the force of attraction, right? So because these are so far away from the pole of that positive nucleus, they feel less pull, okay? So it's going to be, if we look here, it's going to be lower here and higher energy up here, okay? So the highest part of the periodic table is the upper right. Let me just erase a little bit of what I have here so we can see it more clearly. So the high is going to be up here. This is where it's going to be highest, and where it's going to be lowest is in the bottom left. Okay? Hopefully that makes sense. So the trend across a period is ionization energy goes up, and a trend down the group is the ionization energy goes down. Okay, and again, what's happening here, let's take a look at the next picture. This is lithium, I'm going down the first group, right, the alkali metals, lithium, sodium, potassium, rubidium, and cesium. Each time I do that, if I think about it, I've got the nucleus in the center where I have my positive charge, right? And as I add a shell, these new electrons I'm adding are further away, right? They're further and further away, so the force is less strong. There's more space in between the nucleus and the outer electrons. And in some ways, the space and the electrons in here do what's called shielding. They shield the distance itself, plus the electrons in the way, shield that positive attraction to those electrons on the outside. Okay. So here's the trends. This is the listed on the x-axis by atomic number, which is Z, right? Number of protons, and the ionization energy on the y-axis. So if I just look at the first group, here I have hydrogen, and here I have helium. And of course that makes sense. Helium is a noble gas. It's not going to want to give up that electron. It's going to take a big fight, lots of energy to do that. When I get down to the next group, starting with lithium, lithium is going to relatively easily give up that electron because it will become like helium, which is more stable. Beryllium takes more. There's a couple of little blips in here that you don't really need to understand. If we take AP Chem next year, we'll talk a little bit more about why we have these blips. But, you know, the highest ionization energy, again, is a noble gas. The lowest is the one with the one electron. So you can see the big jumps as I add electrons and protons, and I see a smaller decline as I go down the group from lithium to sodium to potassium to rubidium to cesium. There is a drop. There is not significant like the change within a period are. Okay. So let's take a look now. Now, what we've been talking about is really the first ionization energy, but you can remove a second or a third or a fourth or a fifth or a sixth electron for that matter. So let's think about, first of all, I've got sodium and magnesium here, right? They have basically the same electrons, except magnesium has 2 in its outer shell and sodium has 1. So let's think about which of these will have the highest second ionization energy. Okay, so if I lose this electron, then sodium becomes just like, sodium becomes just like neon, right? It becomes like neon. This shell goes away. This outer shell goes away. And of course, neon is very stable. So if I try to remove another electron, I am removing it from the inner full shell. That will be very, very difficult to do. Okay. So it's going to have a very high second ionization energy. Now let's take a look at magnesium. So if I remove one electron, it still has another valence electron. Okay? If I remove a second valence electron, that's going to be even easier because when I do that, now its valence shell goes away. Okay? And you're going to see a big jump when you try to take the third electron off, because when you take that third electron off, you are taking it from what is now the full valence shell, the neon-like shell, right? So the third ionization energy here is going to be very high. Okay. So let's see if you understand it with a couple of examples. So if I look at what's happening here, and I am looking at period 3. So the first element is sodium. First ionization energy, 495 kilojoules. It jumps up almost a factor of 10 to 4,500 kilojoules in order to remove the second electron, because now I'm pulling it off a noble gas. Magnesium, here I have first electron, second electron's about double that, but it's about a factor of 6 or 7 to take off the third, and that is because, again, I am pulling off what's called the core electrons. The core electrons are all of those that are not the valence shell. The valence shell are relatively easy to pull off, but when I pull off the core, I am pulling off the full valence shell electron. Okay, and so you can see this trend for aluminum. First 3 electrons, not so hard to pull off. Huge jump when I get to the 4th electron, because it only has 3 in its outer shell. Pulling the 4th off means I'm pulling it off the core. Okay, no longer the valence shell. So let's try this one. It says, consider the following set of successive ionization energies in kilojoules per mole. And here we have the first electron, second electron. We call them ionization energy 1, ionization energy 2, and so on. And we want to know which third period element do these ionization values belong. So think about it for a second. Pause me, and then come back and and try to answer the question, and I'll explain it. Okay, go try. Okay, welcome back. So what I want to look at is where do we have the most significant jump? So here we're, doubling, not quite doubling, big jump here, factor of maybe 4 or 5, and these are not as big a jump. Okay, so the fourth electron is the one that becomes really difficult to remove, which means I can take off 3 with pretty low energy. And if I'm in the third period, this is period 1, 2, 3, 4, third period, I have to be aluminum. Okay? So actually it's sodium, magnesium, and aluminum. 1, 2, 3 electrons, not so hard to pull off, but if you try to pull, aluminum has 3 valence electrons, not so hard let me go back, not so hard to pull off those 3, but it certainly is hard if I want to pull off a 4th, because I'm going to be pulling them from the inside, right? So this has to be aluminum. Let's take a look at another. Alright, so again, we want to consider the following successive ionization energies, first, second, third, and so on. So let's see where the big jump is. This is almost double, not quite, almost double, 50% more. Big jump right here, okay? So what that says, first 5 electrons, not so hard to pull off. The 6th electron becomes very difficult. So I am an element, again it tells me the third period, where I have 5 electrons, not so bad. 1, 2, 3, 4, 5, not so bad. Whoops. But the 6th is pulling from the core. So if it's the 5 that I can do with a reasonable amount of energy, and the 6th requires a big jump, I must be phosphorus. Okay, so we're going to stop there.